Have you ever wondered how roads survive freezing winters, scorching summers, or relentless monsoons? No matter where you live, roads are a vital part of daily life, connecting cities, communities, and industries. Whether it's the icy highways of Russia, the blistering streets of Dubai, or the flood-prone roads of Brazil, engineers rely on advanced technologies and smart design to keep transportation safe, reliable, and long-lasting. Beneath every smooth highway lies a complex system, carefully built to withstand nature's toughest forces. In this special series on road construction in extreme climates, we'll explore how engineers adapt to every challenge the environment throws at them. This is episode 1, focused on cold climates. You'll learn how roads are built to survive snow, ice, frost heave, and freeze-thaw cycles, using insulation, heated pavements, and frost-resistant materials. Let's get started and see how roads are engineered to last, even in the coldest places on Earth. Welcome to Civil Guru, where we bring civil engineering to life in multiple languages, including English, Spanish, French, Portuguese, Arabic, Hindi, and Tamil. Please select your desired language from the playlist or from links given in description. If you find this video helpful, please like, share, comment, and subscribe to our channel. And if you'd like to support our work, you can now contribute through Super Thanks. Even a small gesture makes a big difference and helps us create more high-quality educational content. Thank you. Let's begin with one of the biggest challenges in civil engineering, building roads in cold climates. In countries like Russia, Canada, Norway, and parts of Alaska, winter temperatures can drop well below minus 30 degrees. In these extreme conditions, roads face a powerful and often invisible threat, a phenomenon called frost heave. So, what exactly is frost heave? When moisture seeps into the soil beneath the pavement and freezes, it turns into ice and expands. This expansion pushes the pavement upward, causing bulges, uneven surfaces, and internal stress. When temperatures rise and the ice melts, the pavement settles unevenly, leading to cracks, potholes, and eventually structural failure. Over time, this freeze-thaw cycle can seriously damage even the most well-designed roads. So how do engineers protect against this silent destroyer? Let's explore the solutions, layer by layer, starting from deep beneath the surface. Step 1. Deep drainage systems. One of the most effective ways to prevent frost heave is to keep water from accumulating beneath the pavement. Engineers achieve this by installing deep subsurface drainage systems, including longitudinal French drains and cross drains. These drains typically use perforated HDPE pipes, wrapped in non-woven geotextile fabric and surrounded by graded gravel to collect and redirect groundwater away from the subgrade. These systems are placed well below the local frost line, which varies from 0.9 to 2.5 meters depending on the regional climate. Above the pipes, layers of filter sand and drainage aggregate are added to maintain water flow and reduce clogging. To further enhance filtration and soil separation, geotextile fabric is used between the natural soil and the drainage layer. This allows water to pass while preventing fine particles from entering and blocking the system. In areas with weak or soft subgrade soils, engineers also install geogrids beneath the base course. These provide tensile reinforcement, distribute traffic loads, and reduce deformation during freeze-thaw cycles. Modern pavement designs an additional layer known as the subsurface drainage layer, SSDL, may also be included. This engineered layer enhances long-term drainage efficiency across the entire road section. Step 2. Insulated road base. In cold climates and permafrost zones, insulating the road base is essential to prevent frost from penetrating the soil and causing heave or settlement. Engineers use rigid insulation materials, typically XPS, extruded polystyrene, or EPS geofoam blocks, known for their very low thermal conductivity. These insulating panels are typically 100 to 150 mm thick, but may go up to 200 mm in permafrost regions, depending on thermal design requirements. They are placed between the subgrade and the base cores, forming a thermal barrier that reduces upward heat loss from the soil and minimizes freezing depth. In high-risk zones, such as in Alaska or northern Canada, engineers may use double-layer insulation, thermal blankets, or vapor barriers to control moisture migration and reduce thermal cycling. These vapor barriers are typically made of polyethylene sheeting or geosynthetic clay liners, GCLs, which help prevent moisture from entering the insulation layer, preserving its performance over time. Advanced road designs often use finite element modeling FMSM to simulate freeze-thaw cycles, allowing engineers to optimize insulation thickness and placement based on local soil properties and climate data. Where insulation is placed on unstable slopes or near drainage exits, engineers may use wire mesh reinforcement or gabion structures similar to chicken mesh to hold stones and soil in place and prevent sliding. Step 3. Heated road systems in special cases. In regions prone to frequent snowfall or dangerous icing, engineers use heated pavement systems to keep road surfaces ice-free and safe. These systems are commonly used on bridge decks, steep inclines, intersections, tunnels, and airport runways where black ice and snow buildup pose serious risks. Heated road systems come in two main types: electric and hydronic. 1. Electric heating systems. Electric systems use resistive heating cables, such as nichrome wires or carbon fiber heating mats, embedded within the pavement structure, either in asphalt or concrete. These cables are typically laid in a zigzag pattern at a shallow depth just beneath the surface. The system is connected to automated sensors that monitor temperature and surface moisture. When snow or ice conditions are detected, the system automatically activates, delivering heat directly to the surface. Electric systems are generally used in smaller zones, such as sidewalks, ramp entries, and pedestrian crossings, due to their quick response but higher energy cost. 2. Hydronic heating systems. Hydronic systems use a network of PEX, cross-link polyethylene tubing, embedded beneath the road surface. These pipes are typically spaced 6 to 12 inches apart, radius 15 to 30 centimeters, depending on the heating load requirements. A heated glycol water solution circulates through the pipes, transferring heat upward to melt snow and ice. The heat source for these systems can be boilers, gas or electric, geothermal systems, or solar thermal collectors in hybrid systems. Hydronic systems are ideal for larger areas like aircraft taxiways, parking structures, and long slopes, as they offer better energy efficiency over time. Though installation costs can be high, these systems provide major safety benefits. They help prevent black ice, reduce accident rates, and minimize the need for manual snow removal and salting. In critical zones, automated snow melt systems are considered a long-term investment in safety, performance, and winter durability. Step 4. Frost-resistant asphalt and concrete final top layer. The final surface layer of the road must withstand extreme cold, moisture, and the repeated stress of freeze-thaw cycles. In cold regions, traditional asphalt becomes brittle and prone to cracking when temperatures drop sharply. To prevent this, engineers use polymer-modified asphalt, PMA, an advanced mix that enhances flexibility and durability. Polymer modified asphalt (PMA) contains 3% to 5% SBS, styrene butadiene styrene elastomers, which give the asphalt rubber-like flexibility at low temperatures. This allows the pavement to flex and recover under thermal stress rather than cracking or shattering. Additional additives like anti-stripping agents to improve bond with aggregates, hydrated lime to resist moisture damage, and crushed angular aggregates for stronger interlocking are often used to enhance performance in cold, wet environments. Despite the modified mix, the standard laying procedures, including compaction, temperature control, and layer thickness, remain the same on site. Frost-resistant concrete pavements. In concrete pavements, the key defense against freeze-thaw damage is air entrainment. Tiny air bubbles, introduced using chemical admixtures, are uniformly distributed within the mix. These microscopic voids provide space for water to expand when it freezes, reducing internal pressure and preventing scaling, cracking, and spalling. Proper air content, typically around 5% to 8% of the concrete volume, is essential for durability in cold climates. As with asphalt, regular placement and curing procedures are followed during construction. The Trans-Siberian Highway in Russia is one of the world's most impressive cold climate road system, is stretching more than 11,000 kilometers across Russia. This highway crosses some of the coldest and most remote terrains on Earth, where winter temperatures can fall below 50 degrees. To ensure year-round performance, engineers here use a combination of deep gravel foundations to maintain base stability, multi-layer thermal insulation to protect the subgrade, and continuous monitoring systems to track permafrost movement and ground temperature fluctuations. These technologies help prevent frost heave, settlement, and pavement cracking, even in severe freeze-thaw conditions. It's a world-class example of how modern road engineering can stand up to nature's most extreme cold. As you've seen, cold region road construction is a highly specialized field, combining thermal insulation, moisture control, and advanced materials to survive the harshest winters. But cold isn't the only enemy of roads. Next, we turn to the other extreme: desert heat, UV radiation, and melting asphalt. In our next episode, you'll discover how engineers battle thermal cracking, material softening, and how road surfaces are designed to withstand scorching climates around the world. Stay tuned, and let's explore how roads are built to beat the blazing sun.